Okay, good afternoon, everyone. We have a couple more slides to go in diodes. We'll wrap up the diode chapter, and then we'll uh, pick up for BJT where we left off. Okay, so let's see. All right, we covered clippers, and we're going to go into clampers. Any questions about clippers? Clipper circuits. Okay. All right, diode clamper. It's part of the wave shaping circuits group of diode applications. Same thing. Let's see. We apply. Okay, hold on. Instead of drawing it again, all right. Let's say we have a sine wave that we're applying to this clamper circuit. Same thing as last time. Analyze using ideal diode model. In the positive half cycle, diode is forward bias. And so it behaves as a short circuit. And when it behaves as a short circuit, it's providing a pathway for the capacitor to charge. Current flows from the power supply, goes to the capacitor through the diode and back, thus completing the circuit. So capacitor is charging, and we'll ignore transient effects for now, right? Because transient effects is basically typically even for a 60 hertz signal, 100 hertz signal, it'll be like a fraction of a second. So capacitor is going to charge up. We're beginning our analysis from the point it has already charged up, okay? So capacitor charges in this direction, meaning it causes a voltage drop across the capacitor in this direction. VC, that's the voltage across the capacitor. So VC will charge up to VP, one peak, right? Positive half cycle. And this is the positive half cycle. What happens in the negative? What happens to the diode? Turns off, right? So because it turns off, let's model it this way. Minus, plus. Now you have a fully charged capacitor. Right? And this is, of course, where we are taking our V out. So what is our V out? We would say negative what? Vs. That's a good starting point. Yes, it would be negative. Yes, but let's say it's V out. And you're not showing any output resistance. Okay. All right. So positive half cycle charges to VP. Capacitor is fully charged. When a capacitor is fully charged, if you measure the voltage across the capacitor as a function of time, what do you see? What kind of waveform would you expect? Capacitor is fully charged. You take it out of the circuit. Ideal capacitor holds the charge constant. If you measure the voltage, you measure it for 1 hour, and you plot it, what would you expect to see? Flat line. The capacitor behaves like a DC voltage source, right? So in the negative half cycle, what V out is going to see is Vs plus Vc. This appears as a battery in series with the voltage source, minus and plus. And this is where we are taking our output. Obviously, because it's in the negative half cycle, the polarities are flipped first, but that's how it looks, right? You're taking V out at this point, which is here. It's capacitor minus plus in series with your Vs, the input signal. It appears as if your input signal added on top of this. Two power supplies in series. And so for every single point in time, when you have the negative half cycle, let's bring this down here. When you have the negative half cycle, your output waveform now has a DC component of minus Vp. So your entire waveform is now shifted down. And you obtain a waveform that looks exactly the same as your input, but now it has a DC component to it. The value of the DC component is equal to Vp. So it's clamped down. Okay, let's take a pause. Think over that. Let me know if you have any questions. Yes. Yes, top waveform is your input. It's a Vs source. It's just shifted down. That's all that happens. Doesn't matter what kind of input waveform we give, triangular wave, square wave, random noise, sine waves, they all appear exactly as they are at the input and the same at the output. The only difference is now it has a DC component to it. And you can plot this one by one. At any given point in time, the sine wave will have a particular value, right? You'll have these dots. So you have these values. You can break it up into 1,000 pieces. So you have 1,000 values representing the entire sine wave. All you have to do is for every single point of that input waveform, you have to add Vp to it, because V out is equal to Vs, sorry, right here. V out is equal to Vs plus Vp. And capacitor is holding its charge constant. Vs is the one that is the negative waveform. So Vs is negative, whereas the capacitor is simply Vp. So if your V in is 0, your output is 0 plus Vp, or I would say minus 0 minus Vp. So your V out is minus Vp, which you see here. Input is 0, output is minus Vp. Your input was plus Vp, which is this point at the top right here. So Vp minus Vp, you get 0. And that's this point right here, because this is your 0 line and this is your 0 line. It's shifted down by Vp, right? And so on and so forth. All right, think over that. Let me know if something doesn't make sense and if you have any questions. Yeah. So if you have a load resistor like this, depends on what the value of the load resistor is. Typically, we would use, so the question is, it's a very good question. If you have a load resistor in there, it provides a pathway for the capacitor to discharge. So the capacitor will start discharging to that load resistor. That's an excellent question. So your capacitor is connected like this, right? So if you now have a resistor A capacitor has a pathway to discharge. The reason the capacitor is not discharging is because the diode is as good as an open circuit. A real life diode obviously has very high resistance. The capacitor will discharge, but it'll be like microvolts perhaps, so small that we could not even measure it. So for all intents and purposes, the capacitor is not discharging if it's the diode. So if you have a load resistor, then we have to, well, design the circuit in a way that the capacitor does not discharge a whole bunch through that load resistor. Does that make sense to everyone? Right. So in EE306, which is the EE semiconductor class, we perform the lab experiment where we do clampers. And in there, we use a load resistor, and the load resistor is quite large value. And obviously, we can also mitigate that. If you want a load resistor that is going to be small, we can always use a capacitor that is very large. Okay, capacitor that is very large. But does the clamping make sense? Right. So this is an example of a negative clamper because the output is clamped to a negative level. From 0, it goes to minus VP. If you want a positive clamper, all we do is we'd flip the direction of the diode. So it would charge in the negative half cycle and it would be off in the positive. So flip the diode. Okay. All right. Any other questions? Now, obviously, the downside of this and the clipper circuit is that we cannot control the voltage. For a clipper circuit, if you just have a diode, it's going to clip everything off except for the diode forward voltage. For a clamper circuit, it's going to clamp at a level of VP. If we want a specific level, then we need to make some modifications. So for a clamper circuit, we'd add like a battery, right? So it only charges to that level. For a clipper circuit, it'd be the same thing as shown here. We'd have a battery in there. So the diode only conducts after that voltage level is crossed. Okay. So the downside of this clipper circuit, of course, is that we require an external DC source. Okay. External DC source is required. So that's the downside of the disadvantage. But the advantage, of course, is that you can, or we can easily vary the DC source, the value of the DC source, and we can change the clipping level as we want. That's the upside. So depending on our application, we could use a single diode or two diodes, or we could use, what else can we use for clipping circuits? What did we do this week? We only looked at one other diode. Zener diodes. We can use a Zener diode. The Zener diode is going to hold the voltage across itself constant. So if your voltage, peak-to-peak voltage is 12 volts, and you connect a Zener diode, back-to-back Zener diodes of, let's say, 5 volts, it's going to start conducting and would not allow or would not permit anything more than 5 volts to reach the output. So it clips the top of that waveform. Okay. One immediate application that comes to mind is using it as a surge protector. Okay. So if you have a single Zener diode rated at 120 volts, you connect it across the power outlets. If there's voltage fluctuations or lightning strike, if the Zener diode can handle the lightning strike, of course, But the point is, if there is voltage fluctuations from 120 volts, it goes like 130 volts, and you want to protect your devices or your appliances, then the Zener diode will conduct, not permit more than 120 volts to go to the output. So that'd be an example of a clipping circuit. But again, surge protectors have far more complicated circuitry, depending on how well made and expensive they are. But the downside of the Zener diode is exactly the opposite of the diode, regular diode. In a regular diode, the clipping level is fixed. If you want to vary the clipping level, then we use an external DC supply. In a Zener diode, the clipping level is fixed, but depending on our application, we can choose. If you want 5 volts, we can use a 5-volt Zener, 6 volts, 6-volt Zener, so on and so forth. And if you want to change, if you wish to change any of that value, you cannot do so easily without replacing the Zener diode. Okay, so both are exact opposites of each other. A regular diode and a Zener diode would be exactly opposite of each other for a clipping circuit. Okay, does that make sense? Any questions before we move on to the last slide? Okay. All right, the last one is photodiodes. Photodiodes. Photodiodes, as the name suggests, has to do with incident photons. Photons. Technically, any diode which is interacting with photons is referred to as a photodiode. But in general, photodiodes are the ones where photons are the input, right? So any kind of electronic device is affected by heat and light. Okay. Fundamentals of semiconductors, we learned that temperature rises from absolute zero. Thermal energy is available for electrons to break their bonds and become free charge carriers, right? So at room temperature, there are generated charge carriers that are free to conduct. Now, if a photon is incident on a p-n junction, that photon can provide its energy to an electron. That electron can absorb that energy and acquire enough energy to break free of its bond and become a mobile charge carrier. That is the fundamental operating principle of a solar cell. You have photons incident on a p-n junction diode. The electrons absorb the energy. They are now free charge carriers enabled to conduct freely. So photodiodes in general are where light is the input. Okay, light is the input to the diode, and then the current and voltage is the output. So the electrons are receiving energy from the incident photons. That's the operating principle of a solar cell. Now, there are some semiconductor materials, like gallium arsenide, for instance, compound semiconductor made from gallium and arsenic. Actually, let me back up. In any semiconductor device, whether it's a p-n junction or a p-n junction diode or a p-n transistor or a MOSFET, FET, any kind of device, you have electrons and holes recombining all the time, right? When electron jumps into an open spot, it's said to be known as recombination. Electron and a hole recombine. When recombination occurs, which is a constant process, when recombination occurs, heat is generated, so that energy is liberated in the form of heat, or is dissipated in the form of heat. So recombination creates energy because the electrons and holes are now giving out the energy. And because that happens, heat is generated. Materials like gallium arsenide, the excess energy, most of the excess energy due to recombination is emitted as photons. And hence we have light emitting diodes. So the light is emitted due to the process of recombination. light emission. Hence, light emitting diodes. Most electronic devices, the energy is dissipated as heat. LEDs, it's dissipated mostly as light, and some of it is heat. And that's why LEDs are more power efficient than incandescent lamps. But LEDs also get hot. It's inevitable. They do get hot. Just they do not get as hot as the whole filament light bulbs. And then we can introduce dopants, different kind of dopants in the semiconductor material. We can have gallium phosphide, we can have gallium arsenide phosphide. There are many different dopant impurities that we can use, and we can tune the wavelength of the emission. If we tune the wavelength of the emission, changing the colors of the emitted light. Actual LEDs have been around for decades. You can buy them for like a few cents. I have like a full cup sitting on my desk of LEDs. So those are the ones we use in the labs for many different experiments. But obviously LEDs are now ubiquitous pretty much everywhere in consumer devices, right? Okay, so that is the end of the material we want to cover. There is some further reading. There's actually quite a bit of further learning if students wish to do that you can learn. It's already there in the class notebook, but I will consider that as outside of the class material. There's only one slide, and I will come back to this when we cover logic gates, if time permits. Again, that's part of the further learning. So for now, call that to be an end and pick up on BJTs. Bipolar junction transistor. Okay. A diode was a single junction device made of two semiconductor materials, P and N. If we create a sandwich structure from this P-N junction or P-N material, you get what is known as the transistor. Bipolar junction transistor consists of three semiconductor materials. If we sandwich, we can get NPN. If we sandwich P, we can get a PNP transistor. Okay. The uniqueness of this transistor lies in the physical construction and the doping profile. The most heavily doped area is known as the emitter because it's emitting charge carriers. In a NPN transistor, that emitter material is N-type, so it emits electrons. In a PNP material, the emitter is P-type, so it emits holes, positive charge holes. Construction-wise and design-wise and operation-wise, PNP and NPN are exactly the same. The only difference is everything is switched. Voltage polarities are switched, current directions are switched because charge carriers are also switched. NPN, primary charge carriers are electrons. PNP, primary charge carriers are positively charged holes. Anyway, so emitter is the most heavily doped material out of the three. Then you have the base. In an NPN transistor, the base is made of P-type material. The base is physically very thin, very small, and it is far less dopants present in the base compared to the emitter. So it's lightly doped compared to the emitter. Just enough doping for it to be considered as a P-type material. So it's not a symmetrical device. Typical PN junction diodes may have perhaps a slight difference in doping on both sides. But in a BJT, the PN junction, the difference in doping is at a far different level. It's a far higher level difference. Okay. So base and emitter is a PN junction. It's a PN junction diode, but the base is very, very small. It's very, very thin. Keyword is thin, actually, not just small. The keyword is thin. So it's very thin, and it is far less doped than the emitter. And then we have the collector region. The collector region, or the collector terminal, is the biggest of them all, and it has the least amount of doping compared to the base and the emitter. So going from the lowest doping level, we have the collector, then we have the base, and then we have the emitter at a very high level. And this uniqueness of the design and the doping profile is what makes the transistor work. It is not a symmetrical device. So in the lab, if you take your transistor and you flip it, you plug in the collector where the emitter was, everything will be the same. Your transistor is not going to get blown out, but it's just not going to work. And I'll get to that point later also. All right. Recap, good? Okay, so then we looked at applications of the transistor. One of the most common applications of a BJT is in using it as an analog amplifier, active mode. And we saw the CE and CC mode amplifiers in the lab. So now let's look at some of the fundamentals. We have the BJT terminals, collector, base, and emitter. And so here we're going to look at the terminal voltages and the terminal currents. Okay. All right. 3 terminals, 3 currents, IE, IC, and IB. Okay. IE, IC, and IB. Now, the uniqueness of the transistor, again, as I said, the emitter is the one that emits the electrons. So current flow is always the opposite of the flow of electrons. So if emitter is sending out the electrons going into the base and into the collector, then current is said to flow from collector to emitter. Okay. And this is referred to as IC. All right. That's referred to as IC. That's the collector current. Now, remember the key word I said in the base was thin. The reason for that thin and low doping profile is that when the emitter and the base junction is forward biased, it's a PN junction, you forward bias the junction, so the electrons start moving from the N-type material, the holes start moving from the P-type material. So emitter is emitting electrons, there are holes in the base that are trying to move in the other direction. Forward bias, we'd expect current to flow through. Well, the current is majority comprised of electrons. The electrons are now coming from the emitter, cross over the first junction, enter into the base. These electrons would recombine with the holes that are available there. But because the number of electrons is far, far greater than the number of holes, there's only a certain amount of recombination that occurs, and most of the electrons are available in that base region. Okay, so that's the first thing that happens. Because of the disparity in the doping profile, there's a large number of electrons that are still hanging around the base with nothing to do, so to speak. Okay. Now, if we reverse bias, and I believe we went over this in, I think, a few weeks ago. If you reverse bias the collector-base junction, well, the collector is collector is N-type, base is P-type. If you reverse bias this, then the minority carriers in the P and N junction are going to cross over. In the base, which is P-type, electrons are the minority carriers. Typically, the minority carriers would be low in numbers. But the electrons that have arrived from the emitter are very large in number. So the actual doping of the base will have a small amount of electrons, but because of the forward biasing of the base emitter junction, a large number of electrons have now crossed over into the base area. And if you reverse bias the base and the collector, the minority electrons from the base are now free to cross over the second junction and go over into the collector region. And that's why even though the collector base junction is reverse bias, a large amount of current is flowing through the device. And that's the basic principle of operation of a BJT. And because of that, because of the low doping of the base, the value of IB is very small. Typically, it's in microamps, whereas the collector and the emitter currents are in milliamps. Okay. All right, let's take a pause. Let me know if you have any questions.
But I don't think we ever talked to users. Like we put the configuration in our lab, but I never understood what the point.
Okay, so the question coming up is about the unity gain amplifier. So I will cover that in, well, probably not today, but next week. Yeah. But a quick answer to that question is, what is the point of a unity gain amplifier? The point of a unity gain amplifier is actually very important in electronic circuits, is to isolate a specific input from the output. So typically what happens in electronic circuits is that we have cascading connections. We'd have an input, then we have some sort of circuit. The input is fed into that circuit. The circuit has an output. That output goes into circuit number 2. Circuit number 2 has an output that goes into circuit number 3, and so on and so forth. As a simplest explanation, I can bring up as an example an audio system. If you take an audio video receiver, you have an input coming into it. It could be a microphone, it could be from a computer, it could be from a phone, it could be, well, any kind of audio signal is going into your audio video receiver. At the front end of any AVR amplifier, there is a preamplifier, more commonly known as a preamp. Okay. Now this preamp is going to take in the signal, right? And its job is to strengthen the signal, meaning its job is to amplify the current in the signal. Not just the voltage, amplify the current that's present in the signal. Now, if it needs to pull in current from the input, let's say the input is just a microphone or like a phonograph or a guitar amplifier for that matter, let's say. The signal is going to be very small, it's going to be very weak. It cannot, that input cannot provide that amount of current going into it. It will have the voltage, meaning it will have the shape, but the current will not be very strong. The voltage and current would both be small, right? So if you have a unity gain amplifier, the voltage is not being amplified, but the current is being amplified. So you have a small amount of current entering with a small amount of voltage. The voltage is basically the shape of the waveform. The shape of the waveform is transferred exactly as it is to the output, hence unity gain. Gain in that sense is simply about V out, voltage output over voltage input. So V out over V in is equal to 1, but the current is not 1. Current gain is far higher. So we are isolating the input from the output. Any current that the follow-on circuit needs is going to come from that unity gain amplifier and not from your input. And that's the point of application of the unity gain amplifier. It's actually a very important configuration in electronics. We use it, we can use op amps to create an isolation or unity gain amplifier. It's also known as a buffer amplifier or an isolation amplifier, where the voltage is not being amplified, but the current is actually the current is amplified in a sense. Okay. It's to avoid something known as the loading effects. You don't want the load to pull in a lot of current from the input. Would not be able to provide that input anyway. Okay, so where was I? Oh, here. IB is very small, microamps, right? Because the number of charge carriers in the base region is very small. So it's very small. typically on the order of microamps, 10⁻⁶, 10⁻⁵ perhaps, whereas the collector and emitter current are in milliamps, orders of magnitude higher, right? At least 1,000 times, if not more. So if we apply KCL, if we consider this transistor as a single same node and you apply KCL, you have current IC coming down from the top. You have IC coming down from the top. You have base coming in and combining with IC. And when we apply KCL at the junction, we obtain IE is equal to IC plus IB. But IB is typically very small. So if it's very small, we can say that IE, the emitter current, is approximately equal to IC. Okay, IE is approximately equal to IC. So for many analyses, many calculations, we sometimes simply take IE is equal to IC. If you want to find say an expression for the gain or analyze the circuit, oftentimes we make an assumption, we just say IC is equal to IE. Okay. But the important parameter between IB and IC is this beta. And for this, let me go over to this diagram on the right. Okay, this is the base, and this is the input IB. Okay. If you recall, I spoke about vacuum tube diodes, right? You have current flowing from cathode to anode, one direction. Same thing. Let's say, let's say you have the collector at the top, you have the emitter at the bottom, you have current flowing through from the top to bottom, right? Now, the external voltage is fixed. VCC, if you're going to apply 5 volts, it's fixed at 5 volts. If you apply 10 volts, it's fixed at 10 volts. So if you don't change anything, if you don't do anything other than apply a DC voltage, you have a fixed amount of current flowing from top to bottom, from IC, from collector to emitter, right? We can't change the value of that current. Once you fix VCC, once you fix the resistors in the circuit, the collector current is fixed, constant line. But now, if you insert a third terminal in there, you can actually change and control the current using this third terminal. And that's what that base is effectively doing. The base is allowing us to control the flow of current from the collector to the emitter. That's the advantage of a 3-terminal device. And so effectively, IB is controlling IC. And I believe we spoke about this also early on in this chapter. IB controls IC, right? Amplification occurs. I believe I may have shown this example also. You have a small input signal that's coming from the base, and you have this large DC voltage applied at the output. Whatever DC voltage this might be, whatever VCC value it is, it's going to be given the shape of that AC signal. So you obtain this at the, well, actually not quite this much. It can't exceed the DC supply, of course. DC supply is 10, you cannot get more than 10 at the output. But you get the idea. Without any AC signal at the base, your output is a flat DC line. But if you now disturb the base and you apply an AC signal, your base current or your base voltage is either going up or it's added on to your base voltage, or it's subtracting from the base voltage. So depending on the AC signal you're applying, your base input current is also changing. The change will be very, 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 very small, very tiny. But the effect on the collector side would be really big. Okay. So that's what's happening. And so that's known as amplification. You're providing a small input into the base, and the output collector is changing in response to that base. So you get amplification. And the base is the input, collector is the output. So the ratio of the output to the input current is known as the current gain. Beta is known as the DC current gain. On data sheets and spec sheets, this is also noted as HFE. HFE. It's a hybrid two-port parameter. Hybrid parameter is basically the forward mode current gain. So HFE. I believe you haven't studied two-port networks, right? 215. So that's where it comes from. Anyway, if you see HFE anywhere with relation to BJTs, simply assume it's referring to the current gain beta. Okay. So IC over IB is the current gain or DC current gain for a transistor, BJT. And the ratio of IC to IE, if you approximately is equal to 1, right? IC and IE is approximately same. So alpha would be approximately equal to 1. Typically, it's always 0.99 something. Okay. 0.99. Alpha is typically 0.99. Beta, depending on the transistor that you're using, could have a wide range. The 2222 transistor has a beta ranging from 35 all the way to like 200 or 300. Very large range. We say that's the typical range. That's what the manufacturer tells us. And the reason, of course, again, simply that when we manufacture or fabricate these devices, we cannot control the amount. We can control the amount of atoms going in it, but we cannot control it beyond a certain point. We cannot control it down to a single atom. It's impossible. Not even to like thousands of atoms, right? Because the numbers we are dealing with is 10 raised to 18, 10 raised to 19, 10 raised to 20 atoms per centimeter cube. So that's a large number. So we cannot control the number of atoms that are going into our semiconductor materials. And hence, there is a large variation. Even for the same transistor, two transistors made side by side at the exact same time, one of them could have a beta current gain of 35, the other one could have 200. It's very easily possible. All right, and then these are two equations here that you can use to determine alpha and beta from each other respective values. Okay, so that's the terminal currents and voltages, output and input characteristics. Output characteristics, let's say this is how it's going to be derived. Okay, so characteristics or characteristic typically means VI or IV. Some authors might look VI, some authors will say IV. Technically, it would be IV because it's current as a function of the voltage. How does the current change in response to a change in voltage? So current on the y-axis and voltage on the x-axis. So in a BJT, you have the input characteristic and you have the output characteristic. Input characteristic is typically the base emitter junction. So it's a forward bias diode. And I have that in a few slides actually. But let's talk about output characteristic. Output characteristic, let's say you have everything is fixed. You have VCC, you have VBB, and you're applying a small input current at the base, right? So let's say that input current is, let's say it's like 5 or 10 microamps. Okay, 10 microamps. At 10 microamps, perhaps there is no change. Too close. All right. At 5 microamps, you're applying VCE. You're measuring VCE, and there's a VCC at the output. Okay. But when you try to measure the collector current, you don't get anything. Right? Collector current is our output. But the base current is so small that we don't see anything. And so we call this the cutoff region, where everything is cut off And we say the transistor is off. Okay, hence it's known as the cutoff region. Now let's say we increase IB. Okay, let's say we increase IB. So IB is now, and I'm going to exaggerate this. IB is now, let's say 25 microamps as we have here. And now we slowly start increasing the collector voltage. We start increasing the collector voltage, the collector current increases in a linear fashion. But it very quickly saturates at a level like this. And from that point on, no matter how much VCE increases, IC remains constant. So it remains like a flat line. Again, IB is 25 microamps. And now you increase VCE on the other side. And you, let's say you take 100 data points. You increase VCE 0.1 volt, 0.2, 0.3, 0.4, 0.5, all the way to like 10, 15, 20 volts. So you have hundreds of data points and you plot them. Well, you'll find that VCE quickly results in a saturation around 0.2 volts. Okay, 0.2 to 0.3 volts. And so IC quickly saturates. The reason we call it saturation is because that value would not change. Okay, it rises linearly for a while. And again, that linear value, probably just a few milliamps. If it's 25 microamps, maybe about 2.5 milliamps, let's just say ballpark. And so then from that point on, it'll remain near constant. It behaves like a constant current source. Anytime you have current constant, it's a constant current source. Now, if you change IB to, let's say, 50 microamps, again, current will rise linearly according to the voltage increase. But again, it's going to saturate very quickly. And once it saturates, the current's going to remain near constant. IBS 50 microamps. And so for every increase in IB, every step that you increase for IB, you can have hundreds of data points for IC as a function of VCE. And so you obtain a set of data points or data curves that look like this. That's what it means. So fundamentally, it's a plot IC, the collector current, as a function of VCE, the collector emitter voltage. But you can have a separate set of data curves for each individual value of IB. Does that make sense to everyone? Okay. And because the current saturates right here to a certain level for every data point, this region to the left is known as the saturation region. Okay, for a BJT, that is known as the saturation region. And this region in the center here is the active region. Okay, and these are the three regions of operation for a BJT: cutoff, saturation, and active. Cutoff, the transistor is said to be off. Saturation is said to be on. So if you combine both off and on together, you can use it as a digital switch. You can use it for digital logic applications, binary number systems. Transistor is cut off, transistor is off, logic 0. Transistor is in saturation, transistor is on, logic 1. Binary number system for digital logic applications. And then when it's in the active region of operation or active mode, we can use it as an amplifier. And we're out of time, so we'll end class here today and we'll pick up here again on Monday. Quiz, as usual, on Monday will be based on Zener diodes. Okay, Zener diodes. Don't think I'm going to have BJTs on there just yet, but I don't know. For now, just Zener diodes. Okay, just doubts. All right, have a good weekend, and I will see you all on Monday.